Welcome back, everybody, to our second lecture of the special lecture series by Alex Lubotzky Lecture Two. Today, Alex will talk about the approximation. Alex, please take it away.
Thank you very much. Okay. I'll start from the problem, and then we'll go kind of backwards, and then the connection with yesterday talk will be clear. It's independent of yesterday talk, but still it's connected. Okay. A group gamma is called residually finite. This is a very standard notion. If for every gene gamma, which is not the identity, there exists an homomorphism from gamma to a finite group such that phi of g is not 1. In other words, you can separate the points of the group by homomorphisms to finite group. So locally, so if you can do it for every element, you can do it for every finitely many, you can separate them from each other, so you can kind of see the group locally. Now, because every finite group can be embedded into the symmetric group, then an equivalent definition is to say that you have an homomorphism to some symmetric group where phi of g is not 0. Now, many groups that you can kind of meet in the street are residually finite. Every finitely generated linear group is residually finite. The automorphism group of the free group is residually finite. The mapping class group is residually finite. But of course, there are also non-residually finite groups, even finitely generated non-residually finite. For example, there are simple groups which are finitely generated. They don't have any homomorphism at all. So infinite simple groups, so they're not residually finite. Now let's see right away the definition of Sophic. This definition was given by the notion was kind of invented by Gromov. The name was given by Benji Weiss. Here we are among friends, we can explain. As Benji explained, it would be natural to call such a group finitary, but he said mathematics is full of finitary of all types. So he called it Sophic, Sophie in Hebrew, but that people will not understand the joke right away. He called it Sophic, that it will sound like Latin or Greek or whatever. There is no word in English which is Sophic. By the way, once he gave a talk at the Hebrew University in a program which called Shnavle Mathematica. It's kind of a program for upper undergraduates, and the title he gave was on Tali groups. It was in Hebrew. And when I read the abstract, it was clear to me that he was going to talk about Sophic. So I said, what is this? He said, well, if the talk is in English, we call it Sophic. If it's in Hebrew, we'll call it Talik or something like that, which is Sophie, finally, in Old Greek. Anyway, this is the notion, which is not so clear why this is interesting to start with. Gamma is Sophic if there exist maps, I stress, maps, not homomorphism, just functions from gamma to sim n, such that for every g and h in gamma, if you look at the limit of the distance between phi n of gh and phi n g, phi n h, it goes to 0. Let me recall from yesterday that the symmetric group comes with the normalized Hamming distance. The distance between two permutations is 1 over n, the number of I in n for which they differ from each other. This is a natural metric. Then the sequence phi n each one of that is not homomorphism, but kind of asymptotically they are homomorphisms. But then we want also that they separate the point of gamma in the following sense. Because you see, if you are just a map and not homomorphism, you can always change something, right, and make it not the identity. But that's not fair. That means nothing. But what we want is that for every G which is not the identity, the lim sup of Dn, phi and G, and then one is the identity of the symmetric group, is bounded away from zero. To start with, it can be dependent on G, but one can prove that if you can do it, you can do it also independent of G, etc., etc. To be honest, the original definition was not like that. It was slightly more geometric, but very quickly people realized this is equivalent, and for our discussion, this is a more convenient definition to work with. Okay, so clearly, if a group is residually finite, then it is sophic. You know, you can really arrange homomorphisms like that. They separate more and more from the group. The most natural, immediate example, which is not necessarily residually finite, are the so-called amenable group. I don't want to stop to arrange those who know what amenable groups, which are kind of the opposite than expander, like they have large subsets such that within the subsets, you take a set of generator which are then they are almost invariant, which means that on a large ball it behaves like homomorphism, and only at the boundary it's not. But if you enlarge the set, then eventually for every two elements this is like homomorphism. Okay, I don't want to stop for that now, but there are many more sophic groups which are neither residually finite nor amenable. So this is a kind of a common generalization of two important notions in group theory. Oops. What?
I just wanted to ask about surface groups.
Surface groups are residually finite, so in particular they are sophic. All linear groups, finitely generated linear groups, are sophic. Yeah, you can define sophic for non-finitely generated, but one can prove that a group is sophic if and only if every finitely generated subgroup of it is sophic. So eventually we can deal really with finitely generated groups. Now, a major problem in a modern group theory is, are all groups sophic? Or this equivalent to the question, are all finitely generated groups are sophic? Why this became such an important problem? It was not like that when Gomov asked it like 40 years ago, but gradually what happened, people prove there have been a good number of conjecture of a problem. Some of the most famous are Kaplansky problems from the 60s, I think, that whether every group satisfies so and so. Okay, and which are still open. One of them, by the way, of the Kaplansky problem was disputed recently. But just at Kaplansky, many problems, there are a good number of problems like that. And gradually, papers came up and said, if the group is sophic, the conjecture indeed is correct. Then we have more motivation to prove that every group is sophic. But frankly, because of all the successes of this notion of sophic, less and less people believe now that all groups are sophic. So I think
What about infinite simple?
What?
What about infinite simple?
Yeah, that's the most natural counterexample, right? They don't have any homomorphism, but maybe they have almost homomorphisms. Not known. There are this crazy group of Olshansky and Briebs. There are the Burger Moses example. There is an Igman famous group which is presented by 4 generators, 4 relations, very simple. It's not simple, but it has no finite quotient. People work on all these examples so far without any success, any success. Very little progress today.
What are examples of Sophie groups where you have the maps which are not homomorphic?
Yeah.
What kind of maps?
What kind of map? For example, an amenable group. Let me give you an example of which a group which you know it is Sophie. You know it's residually finite, but I will show you maps like that. Take Z square, Z cross Z. Take now the ball of radius M. So the number of points there is approximately n equal m square. Now define an almost homomorphism from gamma, from Z cross Z to Sn by acting on the set, by acting on this set of size n in the following way. I have to define you only on the generators. The generators just push it to according to the Cayley graph. And on the boundary, do whatever you want. But the boundary is very small. You see, so these are almost homomorphisms which are not homomorphism. The mistake is kind of is very small. So this is the prototype of amenable groups, and that's what happened with amenable groups. Okay, so you know when we don't know to solve something, the one thing we are very good at is to generalize. What happened here? I don't know something. I don't see page number 3. Okay, I will say it. Here it is. Oh, sorry, it was here. Yeah, it's on the same page. I forgot. Now we know to generalize. How we are going to generalize? Let Gn be family of groups coming with bi-invariant matrix which are invariant by multiplication for both sides. We will say that gamma is G approximated, not residually G Gothic, but approximated, if there exist maps, again, maps, not homomorphism, which are asymptotic homomorphism. What is asymptotic homomorphism? You understand, right? For every x and y in a gamma, the limit in the distance, like before, is going to 0, right? And so this is called asymptotic homomorphisms, and this is called separating. If they satisfy 1 and 2, then they are separating asymptotic homomorphism. It separates the point. So now, what's going on here? So now we say that gamma is G approximated if this happens with respect to this family Gn. And that can be depend on the family. A group can be separated, approximated by one family and not by another. But what are the main examples? The first of all is the symmetric group with the normalizing Hamming distance. Now, if a group is separated, we call it Sophic. That's exactly what we call it. If you can if it's G separated, that's exactly what Sophic. I'm going to give you a few more examples. In all the examples, I will use the same groups, but with different matrix on them. So the same group will be UN, the unitary group, and Dn will be given by some norm where the norm is defined in the following way, but there are many norms that I'm going to define you, but I will use the following notation. If A is an n by n complex matrix, then A star times A is a normal operator. That's easy to see, and therefore it's diagonal and also all the eigenvalues of it are real and greater or equal 0. So we can take the square root of this. And the square root of this we will denote as the absolute value of the matrix A. And now I'm going to define various distances using various norms. The first one, again, the groups now will be always the unitary groups. And then we'll define the Hilbert-Schmidt matrix using the Hilbert-Schmidt norm. What is the Hilbert-Schmidt norm? The Hilbert-Schmidt norm is the square root of 1 over n, the trace of the absolute value of A squared. That's a well-known norm on these matrices. Now, it turns out that if I take a UN with this norm and I ask whether a group is separated, this is another well-known problem in mathematics originated with Alan Kohns. Groups like that, which are separated with respect to the Hilbert-Schmidt are separated, then are called hyperlinear. This is a terrible name because when you say hyperlinear, you think that it is more than linear, but it is less than linear. Like a finitely generated linear group is always hyperlinear, but not every hyperlinear group is linear. So in recent years, they are called Kohns embeddable groups. It's known, by the way, that if a group is Sophic, then it's hyperlinear, but not the other. It's open about the other way around. And Alan Kohns.
But what do you mean linear? It's all linear groups. So what do you mean is not linear or is linear? Is the unitary group?
No, gamma. Gamma is separated with respect to them. You see, your group gamma is an abstract, finitely generated group, and you ask, is it separated by them? Just like in example number 1, we ask, is it separated with respect to the symmetric, with respect to permutation groups? So this is another famous problem. By the way, recently there was a big breakthrough, the famous paper MIP star equal RE. This is the longest paper I ever looked at with the shortest title. MIP star equal RE, which solve Kohns embedding problem in the negative for Neumann algebras. It's still open for group. It's very related, but it's still open. I want to stress this. Okay, let's take another norm. Again, the group is UN. Now we are going to define the Frobenius norm. The Frobenius norm is nothing more. It's just like the Hilbert-Schmidt. I don't know what's. Oh. It's just like the Hilbert-Schmidt, but without the 1 over n, without this normalization factor. So you see, you take the same norm, you just don't divide by n. But you know, all our equations don't go to infinity. So these two sequences are not equivalent to each other. In fact, you cannot deduce now from one to another. Let's do this little exercise. Think about it. Assume you have two different families of matrices on the same group. You know that one group is separated, and let's say that you know that one matrix is always greater equal the other one. Like here, the Frobenius is always greater equal the Hilbert-Schmidt. Assume a group is separated, is approximated in the Frobenius. What does it mean? It means that we have almost homomorphisms in the Frobenius. So there are certainly almost homomorphism in the Hilbert-Schmidt, right? Because Hilbert-Schmidt is smaller. But it's separating in the Frobenius, right? Namely, non-trivial elements are distance away, but maybe it's not separated in the Hilbert-Schmidt. And vice versa, if something is approximated in the Hilbert-Schmidt, then you even don't know that the almost homomorphism, they're also almost information. So this problem you cannot deduce from one on the other, at least in general. Anyway, so this is the story with the Frobenius. Now the Frobenius, the Frobenius norm. And the Frobenius, actually, if you think about it, the Frobenius is basically the L2 norm of the matrix. Not basically, it's equal to the L2 norm of the matrix. But there is the so-called P-Schachten norm, which is basically the LP norms of the eigenvalues. That this is AP, for every P is not a prime. Later P will be also a prime, so maybe I'll try to call it L. P is any number between 1 and infinity, then the P norm is the trace of A, the absolute value of A to the P, and then brackets, and then 1 over P, right? It's like LP norm. P equal 2 is exactly the previous example, but now we have infinitely many, uncountably many P's, and I cannot deduce from one to another. So it's kind of uncountably many open problems of having non-P approximated. The last example is the standard operator norm, and which...
You can interpolate, right?
No.
If you have 2 in the middle,
No.
between 2, you cannot?
No. Think about that. Well, okay, let's be careful. If you know that because the groups are the same UN, if you know that the same group has separating homomorphism to 1, and the same maps is for the other, then you can operate. But if I'll just tell you, an oracle will tell you that a group is approximated by this and by that, I cannot deduce it. It's really... well, in spite of that, toward then I'll say something. Okay, anyway, now let's look at the operator norm. And ask the same problem, just putting the operator norm on the matrices. So sometimes people consider it as the P infinity, P equal infinity. And operator norm approximated groups are called in the literature MF. And this is also a very famous problem of Kirchberg, whether every group is operator norm approximated. In fact, I think that in this case, maybe the expert can help me here, Kirchberg even conjecture that they are, but nowadays people don't believe it anymore. But we'll see. Okay, the main results of today, first of all, is kind of the good news, that in some sense was the breakthrough which started, which brought all this area back onto the table, that there exists a finitely presented non-Frobenius approximated group. This was a joint work with Marcus de Chiffre, Leb Glebsky, and Andrea Thom. Shortly after that, I proved with Itzhar Oppenheim from Ben Gurion that there exists even a finitely presented group which is not approximated for every P between 1 and infinity, bigger than 1 and less than infinity. The method was I'll explain, was similar to that, but some cohomological condition was needed, but in principle it was, and we could even say the same group, which usually that's not the case, but this was not. So after these two works, which took part a few years ago, from all other examples, all problems were solved. Uncountably many problems were solved, and 4 were left. Are there non-Sophie group? Are there non-hyperlinear group? Are there non-MF groups? And what happened with P equal 1? Very recently, like a few months ago, I'm sorry, after the talk yesterday, I realized it might be better, especially for the audience, that I use slides. I don't know to prepare them myself, so I took a little old slides. Quite recently, a few months ago, together with 2 students of mine, we solved the problem of P equal 1. We also P equal 1, there are non-approximated group with P1.
All these are explicit constructions.
Explicit construction. Yeah. We tried random group, nobody knows what the situation with random groups to all of them, yeah. So this, it's kind of amazing that exactly these three famous problems were left out. Believe me, I would, so this is a theorem, this is, if you want, this is a union of uncountably many theorems. I would replace all of them by one of these three, which are really famous old problems: the MF, the hyperlinear, and the Sophic and the MF. But anyway, this is a progress which at least gives some hope for this. I don't know what will happen. You will see in a minute. So now the proof uses stability that I talk about tomorrow. Now you remember what we had, I talked about tomorrow, I said, yesterday. You remember what we had yesterday. We have a set of equations, which is really a subset W of the free group on D generators. And we look at the group gamma, which is the free group divided by the normal closure of W. And we call the group stable if the equations are stable, namely if every almost homomorphism is near, if every almost solution is nearby a solution, right? But now think about it. What does it mean, a solution? You take a solution of W in the symmetric group, or a solution of W in any group, like Gn, Un. What does it mean? It means that I pick up D elements from the group, and a solution means that they satisfy W. If they satisfy W, this exactly means that there is an homomorphism from gamma to that groups, right? That's exactly the meaning, right? If you take a group generated by generators and relations, you have another group. You send the generators to the other group. This defines an homomorphism if and only if the relations are satisfied there. Which means that almost solution is basically what we call here almost homomorphism. It's synonyms, it's the same thing. I could use this language. I don't want to stop for that, but think about it. I prefer to use the other language with infinitely many and sequence because this definition works only for finitely presented group. The definition I gave today, well, I didn't give yet stability, we'll say it in a minute, works also for finitely generated groups which are not necessarily finitely presented. Eventually we don't need it, but it was kind of nice to have the notion also for any finitely generated group, not just for finitely presented. Okay, so now let's define what is the meaning to be G stable, and you see that it's exactly, for finitely presented group, is exactly to say that the set of equation is stable in the way I defined it yesterday. But if you were not here yesterday and you didn't watch the talk, then doesn't matter. This will be independent. So let's Gothic G be the family Gn and Dn as before with matrix. Gamma is any group. We say that gamma is stable. Gamma is stable if G stable. So this is with respect to G. I stress, you remember yesterday I told you that two matrices are, the commuting is stable with respect to the Hilbert-Schmidt norm, really, and it's not stable with respect to the operator norm. I mentioned this. So it's really with respect to the family we are talking about. So gamma is G stable if whenever we have phi n from gamma to Gn asymptotic homomorphisms, If the group is finitely presented, you can think about it as almost solutions. Then there exist true homomorphisms from gamma to Gn, which are very nearby. Namely, for every G in gamma, dn of psi n of G and phi n of G goes to 0. Okay, this is a stability of this is G stability. Now, I mentioned yesterday, I will not repeat it, but there is a close connection here with the computer science notion of test stability. And I want to stress that it's not completely the same, but I don't want to stop to work it. We worked out in a paper with Oren Becker and Mosayev. We worked it out several years ago, what's exactly the connections. It's possible for a group to be testable without being stable because the test is different than the natural one. But I don't want, this is for Noga, for you. Okay, now the starting point of the proof of the theorem is an observation made 20 years ago by Lubotzky and Riviera, which is a trivial observation. Probably, maybe it was known to experts at that time, which appeared in the Taiwanese Journal of Mathematics. This is the only time I happened to look at a paper in this journal, which is very simple, but it's very, 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 very influential. So again, I give them the credit because they put it in print. Some experts tell me that it was known at the time. I started to be interested in all these subjects only something like 10 years ago, so I really don't know the history. But they say, here is the proposition. Let G be one of the above examples, and gamma a finitely generated group. If gamma is G approximated and G stable, then it must be residually finite. I'll give the proof, but let's jump to the corollary. The corollary is that if gamma is finitely generated, G stable and not residually finite, then it is not G approximated. That's what we want to achieve, right? You want to find groups which are not G approximated. That's the whole issue. Okay, what's the proof? Proof is trivial. Assume gamma is G approximated. What does it mean? It means that you have separating asymptotic homomorphism from phi n to Gn, right? This is just the definition of being G approximated. But if it's also G stable, then you can move them a bit, the phi n, you can change them a bit to get homomorphism. And you think about the definition, you see that if you move them a bit, it's still separating. So you get separating homomorphisms. So you can separate gamma by homomorphisms to Gn. Now, in the first example, that the group are Sn, this already means that it's residually finite. You can separate the points by homomorphism to the symmetry group. In the other cases, which are Un, you have to give another line. So gamma is separated by homomorphism to finitely generated linear groups. But finitely generated linear groups, we said, are always residually finite. So you can separate your group by homomorphism to residually finite groups. It means that you can separate the group by homomorphism to finite groups. Okay? That's all. So now,
You mentioned all the time two specific families, vector groups and
right.
UN.
So it's more than two. It's uncountably many. It's only two families of groups, but with different metrics. And I said different matrix make the whole subject different. Now this, I mentioned it because this was kind of the classical example that people study. Yesterday, a few people asked me, there is another example which was studied very, very, much less. Maybe there are in the literature, I don't know, 3, 4, 5 papers about it, and this is the rank matrix. You take UN, or you take any GLN over every field, and you find, you take two matrices in GLNF, and you define the distance between them by 1 over n, the rank of A minus B. This is also an interesting example. Very little is known about it. It's known that if you are separated in the rank sense over some field, then you must be sophic. That can be no, the other way around. Sorry. If you are sophic, then you are separated by other. So if somebody would prove that non-approximated with respect to the rank, it will be wonderful because it will give non-sophic groups. Basically, that's the only example. But of course, you can choose your own example. I mean, so little is known. In some sense, what I present you is the first time that some non-trivial theorem will prove for non-approximation.
I'm asking about this Lubotzky statement.
They talk only about the permutation. At that time, they were interested only about the permutation, but the proof is exactly the same.
In all cases.
What?
In all cases.
In all cases, no. Okay. If you use unitary group, if you use GLN, the rank group, if finitely generated groups of the GN are residue finite, then it's the same thing. But if you come up, I don't know, with some crazy. What? This is a theorem of Maltsev from I don't know, almost probably. Finitely generated linear groups are residue finite. Yeah. Okay. Okay. Now, the problem with the criterion of Lubotzky and Riviera, it is much easier to say than to do. How do we find groups which are G stable? As I tell you, it was a theorem by Argestreva and Penesco that Z cross Z is stable with respect to permutations. That's one single case. I mentioned yesterday that we have now a much stronger criterion for group to be permutation stable with the IRS, with the invariant random subgroups, but this criterion is for amenable groups. Amenable groups are all sophic. So it's not going to help us to get non-approximated group. The key breakthrough which came up, quite surprisingly, I have to say, we were surprised ourselves to describe it. By the way, it was amazing that more or less at the same time, Tom and his student, Schiffer, and Lubotzky and I get to the same criterion, more or less. And then we met in a conference, and when we decided to join forces. So here is the criterion, which you will find it strange, I guess. Assume gamma is a finitely generated group, and assume H2, the second cohomology group of gamma, which coefficient in V is 0 for every unitary representation of gamma on any Hilbert space V. Out of the blue, suddenly we have vanishing of cohomology coming into the game. Then gamma is stable with respect to the Frobenius norm. The surprising thing is, which I'll try to explain in a few minutes, is what to the LH2 vanishing of cohomology has to do with the problem. I will postpone this for a few minutes, and then I will show first how to use it. Believe me for that, and how to use it. By the way, do you know what is, have you seen the following condition, that H1 gamma V is equal 0 for every unitary representation of gamma on every Hilbert space? Have you ever come across to this condition? So this is an hint toward the title of the talk. H1, vanishing of H1, the first cohomology for every unitary representation, is equivalent to Kazhdan property T. As some of you may know, Kazhdan property T is the, I would almost say, the standard machinery to get expander graphs. H2, vanishing of H2 is an in to go higher, to high-dimensional expanders, right? So let's do it.
Before you continue, is there a cohomological obstruction for the operator node that you know?
In principle, yes. In principle, the same thing if you know that H2 gamma equals 0 for every Banach space, then you get it. The problem is that it seems that for the operator norm it's never happened. For every Banach space. So that's why, yeah, we'll see in a minute. Now we are going to the high-dimensional expander and to Garland theory and local to global results about expander. So let me, might be a bit too quick to go just to the next. Let me say a few things on the blackboard here. I guess most of us know the following situation. If you look at the group SL2R and you divide it by a maximal compact subgroup, in this case this is SO2, it's a maximal compact subgroup. So this quotient space is the upper half plane, the famous upper half plane with the hyperbolic plane. If you take SLNR, or more generally any simple real group, and you divide it by the maximal compact subgroup, you take the so-called symmetric space associated with the Lie group, and there is a lot of harmonic analysis, geometry, etc., studying this group by these spaces. The monumental project of Bua and Titz, really monumental, was to do a theory like that for p-adic groups. I must tell you, I grew up already after they did it. And at some point, like, I don't know, maybe 20 years ago, the Abel committee, Titz got the Abel Prize, and the Abel committee asked me to give a public lecture after the ceremony for mathematicians, but someone to explain why that. So I went to study. And I realized that this is a monumental work which came from nothing in some sense. They took p-adic groups of the p-adic. P-adics have nothing continuous, right? How do you have a geometric structure on p-adic groups? They created the theory, maybe not from scratch, there have been some people who had some. First of all, the simplest example is SL2QP divided by maximal compact subgroup. In this case, this is the P plus 1 regular tree. But if you take general group over the p-adic, like SLN QP, maybe I'll call it QL, because we already used P for the other, and SLN QL divided by a maximal compact group, you get the Boatitz building, which is a infinite contractible simplicial complex of dimension equal n minus 1. You see, for SL2, we got dimension 2 minus 1, dimension 1 at 3. For SL3, we get dimension 2. For SLN, we'll get higher dimensional simplicial complexes. Okay? And there is a huge theory about this. The maximum compact in SL2 is SL2ZP, the p-adic integer. But you see, this is what the difference? The difference is that this has a structure. If you take SL2ZP in SL2Cupid, wonderful question, SL2ZP is an open subgroup. It's compact, but it's open. So the quotient is discrete. There's no structure. There's no geometry. You have to invent it somehow. That's really amazing. You see, there are like 70 theorems which follows just from the fact that you have this structure. For example, take a lattice here to say what is the cohomological dimension. It follows immediately. Things which without this structure of the Boatits, you can never know. It's really an amazing, it's a monumental piece of work, which is not something, I don't know, here we feel it's kind of a God-given, right? Here you may feel that it's really human invention somehow. I don't know. Anyway, let's continue. Now, at some point, Jean-Pierre conjecture. Now, there is a notion of a group, of a rank of a group. The rank of a group in this case is n minus 1. And this is the rank is the dimension of the building. Serre conjecture that if gamma is a co-compact discrete subgroup in such a p-adic group, and let's say that the rank, or if you want, the dimension of the building associated with GQP is, say, D, then the cohomology of, that all the cohomology of gamma with coefficients, I think he conjectured it only for trivial coefficients, is equal 0 for every I between 1 to D. Vanishing of cohomology. Now, this vanishing of cohomology, because this space, now think about it. If gamma is discrete co-compact, then if you take the Boatits building and divide it by gamma, this is a finite simplicial complex. And because this is contractible, it's well known the cohomology of the group is the same as the cohomology of this finite simplicial complex. So altogether, this is about finite simplicial complex. Garland came to the game in the, I think, early 70s, and he proved Serre conjecture. His proof, at that time, he didn't use this language. It was a local to global expander. And what is now the computer scientists doing all the time? Noga can confirm. But it's all going back to Garland. I mean, he did it in a different language. And he proved vanishing cohomology, but gradually people started with him, and maybe the most general, not the most general, but at least for unitary representation, Bolman and Svetowski in 97 proved the following. Now, if G equal GQP, like SLNQP, QL should be really, is a p-adic Lie group, so that the rank is R. That the rank is equal over to the dimension of the building. That's the Boatits building associated with G is greater or equal to. Let gamma be a co-compact lattice, discrete subgroup which is co-compact. Therefore, as I explained, B mod gamma is just a finite simplicial complex of dimension R. So this is a theorem about a finite object. Then, at least if P very large, now that there are better and better results, I don't want to go to that, the HI vanish for every unitary representation. You remember what do we need? H2 vanish. Wonderful. There are plenty of groups that the rank is more than 2. We are getting, from this theorem, plenty of groups where H2 vanish for every unitary representation. Gala, by the way, proved it only for finite dimensional. They extended it, but what we need already was waiting for us on the shelf already from 97. But there is one problem. These lattices are finitely generated subgroup of the p-adic groups, which means that they are residually finite. Maltsev theorem. But what do we want? We want to get none Frobenius approximated. Every residually finite group is Frobenius approximated. What do we do? Well, I tell you, these are all linear residually finite. This is, when I work on this, it was the first and maybe the only time in my life that I felt that maybe being old is better than being young. Why? Because I was old enough to remember a little results by Delin. which I never really understood why the big Deligne was scared about that. But he proved the following theorem in 78. He showed that if you take some non-uniform arithmetic lattices in the symplectic group 2G over R, then this little group, this gamma, has a finite cover, gamma tilde to gamma, where Z is gamma, where Z is finite and central even, and gamma tilde is not Resdoli finite. To be honest, I didn't understand why he did it. I asked, some people explained it, I don't know, I didn't really understand. Later on, in fact, the reason I remember about that was that Raghunathan extended to co-compact uniform lattices. He used the congruence property, something that I was interested in, and Toledo used this to solve a long-standing problem by finding a non-Resdoli finite group, which is pi 1 of some projective variety. So it came to a good use. Now, what we did, we imitate the Deligne over the p-adic. I want to give credit to Dave Witt-Morris. Deligne work I was not able to understand, and not because it was written in French. Because it used the language of algebraic geometry, which was very difficult for me. But luckily, I realized that Dave Witt-Morris gave a talk on that somewhere, and he was kindly put the notes of the talk on the internet. And it was not only in English, but it was in the language of algebraic group, arithmetic group language, which I can read. So we went and we proved exactly the same theorem over the p-adic. Let G equal SP 2G symplectic group with p-adic coefficients, gamma arithmetic co-compact lattice, then there exists such a finite cover, finite gamma tilde, map onto gamma with Z finite central, and gamma tilde is not residually finite. Aha. Now we have it, right? Because for gamma, we have vanishing of H2. Vanishing of H2 goes from gamma to gamma tilde. That's the standard argument in cohomology, central spectral series, that the vanishing gamma tilde. Now, and therefore it is what? Frobenius stable. So we have a group which is Frobenius stable and not residually finite. If it's not residually finite, then it's not Frobenius approximated. Now I should tell you, the breakthrough in some sense in all this work is not to look for simple groups. You see, like all the world before that, we were looking for groups which are far away from residually finite. Simple groups, Higman group. Here the group is almost residually finite. You see, the group gamma tilde, if you can separate almost all the points, except actually you can make it Z even to be of order 2. Except of one element. The kernel you cannot separate. So crazy, the group which is closest possible to being residually finite, this is the one which we prove is not approximated.
So it's a very weak example.
It's a very weak example in some sense, right? Yeah. But it's an example of a non-approximated group, right? It's probably true what you suggested. We also tried. We never succeeded. With this one, we succeeded. Anyway, the work with his R to do it for LP was really by proving the vanishing cohomology for suitable Banach spaces. I will not go to that because in the last few minutes that I have, I want to explain what's the connection with H2. We understand that for H2 we need high-dimensional expanders. Tomorrow I will come back to this wonderful, this is an amazing simplicial complex, believe me. It's kind of an unbelievable object, this simplicial complex. But in the last 2-3 minutes, I just want to explain how H2 suddenly came into the game. Okay, so, and that's completely general. Assume phi n from gamma to the unitary group are asymptotic homomorphisms. And let's take U capital U be just the direct product of them. That's the direct product of them. So this is a huge compact group. Let U bar be the topological ultra product of them. What does it mean? Well, I guess that here, I guess you're responsible that people in Haifa knows about ultra product. Even the secretaries, I checked with Michal. Everyone knows. Okay, if you don't know, it doesn't matter so much. Think of it in the following way. We take U and we divide it by all the sequences so that the distance converges to 1. The right thing is converge in the sense of the ultra product. That's the right thing to do. But assume you divide it by something like that. Now, this is an awful group. It's not a closed subgroup. What?
Non-principal.
Not principal group, of course. Yeah, sorry. This is an awful group. For example, K, it's not closed, and it's actually dense in U. But it's normal. You can divide by it. You get a very ugly kind of quotient. Okay, but now think about it. Assume you have, you start with phi n, which are almost homomorphism from gamma to U, then they induce one homomorphism to the quotient, because I exactly divide by those which convert to the identity, right? So every sequence of almost homomorphisms induces one homomorphism. Suddenly we are back in the category of groups and homomorphism that we feel more comfortable with. You see, almost homomorphism is a terrible notion. What is the kernel of almost homomorphism? What is the image? You can always change it a bit, right? But now we move to a single homomorphism to a terrible group. You know, there is no free lunch in this world. But at least we are in the category we are more familiar with. Now another trivial observation. Gamma is stable if and only if you have such a phi from gamma to K, you can lift it back to U, not to the original one. Of course you can lift it back to U, to the original, but you can lift it to a homomorphism, to a true homomorphism from gamma to U. If you think about it for a second, this is exactly equivalent to stability. Because stability means that you can replace each one of them by homomorphism, so you can lift back the homomorphism. You can lift up the homomorphism from gamma to U mod K to homomorphism from gamma to U. Now this should ring a bell, because now this is a problem in classical mathematics. There are many problems like that in the inverse gamma problem of lifting homomorphism. You have an homomorphism to a quotient. You ask yourself, can you lift it up to homomorphism to the bigger group, right? Now we are back into area that we know what we are talking about. What's the problem? The problem is that this kernel is awful. When we know to answer such problem, we know to answer such a problem if the kernel is a billion. If the kernel is a billion, then H2 is exactly, so we need to solve a lifting problem. The problem is that K is very nanobillion. And here came a trick. What we observe, that if the norm is submultiplicative means that the norm, you remember everything starts with a norm, that if the norm is at most A times B, the one we work. So all the LP are like that, including P infinity, the P infinity problem. But the Hilbert-Schmidt is not like that. The rank is not like that. You see, so, but if it's submultiplicative, then K can be approximated. The kernel can be approximated by a sequence of a billion extensions of Hilbert spaces. So this is a bit technical, but not complicated. I mean, it's a one-page proof. Those who love congruent subgroups like me can see an int. Uri, that's for you. if you look at group like SL3Z, and you look at the congruence subgroup mod P, it's a very non-abelian group, right? It contains 3 groups. But congruence subgroup mod P modulo congruence subgroup mod P square is abelian. And P square over P cube is abelian. And this is abelian. So there are many, many abelian. You can kind of abelian. And this is all together within a compact group, so you can kind of take a limit and solve it. So you kind of split the problem. Instead of working with a huge non-abelian group, you work with a group that you can cut into small pieces that each one in abelian. Now, if you have an abelian quotient, and moreover, because we divided by the ultra product in this machinery, we get Hilbert spaces in the case of P equal 2 and some Banach spaces for the other P. Now, if H2 vanish, it's exactly the machinery to solve such lifting problem. The vanishing of H2 enable you to solve the abelian pieces, and that's proof of theorem A. Theorem B, you have to know, you have to extend the Garland theory from unitary representation on Hilbert spaces to isometric linear representation on Banach spaces, and is R is the world star, is the world leader of this direction. In fact, after we did it, I called Izar and I told him, I need your service, I'm sure you can do it. And then I called him, we met, and he said, yes, I believe it should work. Okay, so that's why, and, okay, I promise you something about P equal 1. P equal 1, only recently we managed to prove it. We don't know to prove that some groups are stable P1, but in spite of what I told you, that I cannot compare with different norms, different matrix, if a group is of the Lin type, namely just finite, you can say something. And we realized it only very recently. In fact, I would admit that we wanted to solve the MF, because in the MF you feel like you have the machinery. We wanted to connect it with something else, and then we kind of wanted to do this. We failed, but luckily in mathematics, sometimes you can present failures as victories because we realized that it proves something else. So we finished with the case P equal 1, and the 2 big problems are still waiting.